Okay, so today we're talking about relative rates of growth, and I need to give you a little disclaimer on this. First thing you need to know is that the graphs that we study today all have to be eventually ending up in the first quadrant. So here's what we mean. A graph like today would be, a graph in our discussion today would be a graph like this one, or a graph like this one, or maybe a graph like this one. Okay? These graphs are to be discussed today. What you'll notice that all three of these have in common is that their right end behavior, see that arrowhead? Let's give that guy an arrowhead too. All of these eventually end up in the first quadrant. Now a couple of them took a little dipsy-do down in the quadrant, the lower quadrants. Like this graph spent a little bit of time down below here. Quite a bit of time, actually. This graph spent a little bit of time down below here. But after a certain value of x, it rose up above the x-axis, and it never plunged back under the x-axis ever again. Okay? So the graphs that we cannot talk about today are graphs that are like sine waves. Why would sine not count today in our discussion? It's because sine never really decides to stay in the first quadrant. Sine does this, you know. It keeps going back and forth between quadrants 1 and 4. So we're just not going to discuss that kind of graph today. Okay? All right, so this graph would be off topic. So how do you summarize that? You would just simply say, let me word it for you. Today we consider functions that are entirely positive after a certain value of x. Okay. Can anyone else think of a graph that it goes and eventually spends the rest of its life, maybe it's underneath for a while, but it spends the rest of its life above the axis?
Square.
What's that?
X squared.
X squared, yeah. X squared does that. Spends all this time in quadrant 1. After x equals 0, it's always in quadrant 1. By the way, after x equals 0 means to the right of. Right? So left is before and right is after. So it goes up and then it stays up. X cubed is that way. Square root of x is that way. A lot of these graphs are not sine and cosine because they keep going back down into the lower quadrants. So we can't discuss those today. Okay? All right, so the title of the section is basically relative growth rates. What we're trying to understand is what functions are growing faster and which functions are growing slower. So I don't think this is going to be very hard for you to understand. Most of you know that e to the x is a very quickly growing graph. Okay? But here's a question. Which grows faster, e to the x or 2 to the x? Okay, e to the x? Okay, are you saying that because e is 2.7?
Yes.
Fair enough. Okay, so which grows faster, x squared or x cubed?
X cubed.
X cubed, are you saying that because power 3 is bigger than power 2?
Yep.
Okay, so which grows faster, y equals x or y equals 2x? They have the same growth rate. So what you think growing fast means is not quite, listen, what you think faster growth rate means is not quite right. Okay? So today I'm going to tell you exactly how you can tell if one function is growing faster than another. All right, so here are the rules of the day. These are the definitions. This is how we play the game. Okay? F grows faster than G if, here's the rule, LIM, x goes to infinity, f over g is infinity. This is the test. So no more guessing. Okay? If I say, show me that f grows faster than g, you don't say, well, e to the x grows faster than 2 to the x because e is bigger than 2. No more. We're done with that. We're going to use this test. So we have a really solid test we can hang our hat on. Okay? Let's think about what it means for a minute.
let's take two graphs. One is obviously growing faster than the other. So imagine with me if f was just this graph x. So f of x equals x. That's simple enough. F of x equals x. And let's do for our second graph, g of x equals rad x. I'll bet you could tell me which one grows faster. Look at the graphs, right? Here's f of x. It's a nice straight line, right? Here's g of x. Not so straight. How many of you would assume that f is growing faster than g? Okay, it is growing faster than g. It's easy to see that. If you go out here at 1, they're both the same height. But if you go out to, let's say, 2, this graph is at 2, rad 2, and this graph is at 2, 2. The y-coordinate is certainly larger, right? F has the larger y-coordinate. But that isn't good enough for us to say that f is growing faster than g. You have to show me that that behavior not only continues, that f is bigger than g always, but that f divided by g is growing. Okay? So for example, you cannot tell from one point that we have growth. 2 divided by rad 2 is, well, it's about 1.4. If you go out to 3, it's now these two red dots. So this would be at 3 rad 3, and this would be at 3, 3, see? And the ratio of 3 over root 3 is bigger than the ratio of 2 over root 2. So the ratio is growing, you see. That's proof that we have f growing faster than g. So this is the only thing I can accept. You cannot say x is growing faster than g because x means x to the first, and g means x to the half. And first power is bigger than half power. No. Do this calculation. Let's do it real quick. It's really easy. So I'm going to prove right now that f grows faster than g. Here's the calculation. Just do a simple limit. Okay? So this is just, you can use l'Hopital if you wanted. But this is x to the first, and this is x to the half. So when you subtract, 1 minus a half is, of course, a half. So I'm showing way too much work for this problem. And then just answer this limit question. What happens to rad x as x gets big, it gets big? So see, I got infinity, which means f grows faster than g according to my rule of the day. This is rule 1, okay? Rule 1. Circle it. This provides us a test for who grows faster. It's also an important chapter 9 concept when we do series and sequences. This was just my first example. I chose x and rad x. Okay, any questions so far? Okay, now how would you know if f was growing slower? So I don't want to make a separate rule for this. In what condition, or what would be the limit if f were growing slower? Another way of saying that is g is growing faster. Now if the denominator is growing faster than the numerator, this isn't going to go to infinity. It's going to go to what? 0, correct. So this rule can just as well be interpreted as, you can read it in the red instead of the black if you want. So f grows faster than g if this limit comes out to infinity. F grows slower than g if this comes out to 0. Okay? So that's like rule 1, and I guess rule 2 all wrapped up into one rule. Let's take a look at a second rule. What happens if you don't get infinity or 0 from this limit? Rule 2. F and g grow at the same rate. F and g grow at the same rate if you do this limit. Notice it's the same exact limit, but you get a non-zero real number. This is rule 2. Okay, rule 2 is sort of the only other possible case. Either f grows faster than g and we get infinity, or g grows faster than f and it comes out to 0, or it doesn't. And it comes out to something that's not 0 or infinity. This is like the third possibility, and we call this growing at the same rate.
So that's why x is 2x plus c.
Yes. So what I want you to do is put this phrase in quotations. Grow at the same rate does not mean the two functions look exactly the same. It just means that this limit comes out to a number. That's what it means. Okay? It's really important you understand that. So that is a very important phrase. If you see it on the AP test, it is not just, hey, which function looks like it grows faster. If you see that phrase, they grow at the same rate, it means this limit is a number. Okay? Okay, so let me show you some examples of that. Excuse me. Show that f of x equals x and f of x, g of x equals 2x grow at the same rate. That is not obvious to me. I mean, if you look at the graphs of these things, right? Why are we saying that f of x and g of x are growing at the same rate? They don't look like they're growing the same rate at all, but they are. And we can show that by doing this limit. So we're taking all the guesswork out of it. We're just going to do this, Lim, x goes to infinity. You can do f over g, or you could do g over f. It doesn't really matter. Let's do f on top. This reads, limit as x goes to infinity, x over 2x equals, and what does this limit come out to? It comes out to a half. Is that 0? No. Then g doesn't grow faster. Is it infinity? No. Then f doesn't grow faster. Is it a number besides 0? Yes. Then f and g grow at the same rate. So 1/2 is a non-zero real number. Therefore, if you ever see 3 dots and you're wondering what they're there for, they mean therefore. Okay? So this is the logic symbol for therefore. Therefore, f and g grow at the same rate.
But there's 3. Shouldn't be 4 dots, there 4. That's there 3.
F and g grow at the same rate. That's what we say. Actually, I think it is interesting that there are 3 dots there. I've often wondered why 3 dots. Maybe it's because the first 5 letters of therefore are also the same letters as the word 3. C-H-E-R-E. T-H-R-E-E. I don't know. Could be the same. Could be why. That's not a hard rule, right? You're just taking one limit, and depending on its outcome, you're making your statement. Let's try this one. What about e to the x and x to the 100th? So we'll call f e to the x, and we'll call g x to the 100th. And the question is, of course, which grows faster? That's the whole topic of the day, right? So which grows faster? Or which has the faster growth rate? Well, x to the 100th is awfully steep, and e to the x is awfully steep, and the answer is e to the x. F grows faster. But I don't have to guess and check. I can actually prove this by doing one limit. So I'm just going to take these, and I'm going to put either one on top. Doesn't matter. I'll just do f on top again. If this comes out to 0, I'll say g grows faster. If it comes out to infinity, I'll say that f grows faster. If it comes out to some number, I'll say they grow the same. It's that simple. except for one little thing. How do you solve it?
You don't.
You don't?
It doesn't exist.
That's profound. No, we're going to solve it. What kind of problem is it? Is it 0 over 0? What is this thing?
It's infinity over infinity.
This is infinity over infinity style, right? Can we use L'Hopital's rule? Okay, so let's try it real quick. It's kind of fun. Let's take the derivative of the top. What do we get? Yes, e to the x. What do you get for the bottom? 100 x to the 99. So that was L'Hopital's rule. Let's do it again. We're going to get e to the x, 100 times 99 times x to the 98th. Let's do it again.
Can't you just do x? 100 factorial x?
Yes. Hunter sees a pattern. E to the x is on top. Then I have down here 100 times 99 times 98 x to the 97th. You know, it's still kind of hard to compare these, right? I would like the bottom to eventually just be a number, the top should end up changing. I would need to do a lot more derivatives. But what would this coefficient be? It's going to be 100 times 99 times 98 times 97. That's going to look like 100 factorial when I finally get down to x to the 0. Correct. So this is going to go on for quite a while. And just using inductive reasoning, we can assume that this is going to end up to be 100 factorial on the bottom. And now I think it's very obvious that this goes to infinity. Right? The bottom's a number. Yeah, it's a big number, but e to the x is an unboundedly large value, right? There's no boundary to how big it can go. So this is finally truly clear to me that this is infinity, and the rules of the day, rule 1 says f grows faster than g. Therefore, f grows faster than g. Now I had a gut feel that e to the x grew faster than x to 100, but a gut feel will never pass on my test. I cannot say, oh yeah, you're right, f grows faster than g. Nice gut feel. Okay? This is it. This is your only proof. This is what you have to show me. Okay? Including the ... and maybe you can just write inductive reasoning here. And I'll say, oh yeah, you understood that. Okay, let's go to the next one. ln x and rad x. Now these guys are both slowpokes. Okay? That last problem, those guys are both pretty quick. They grow pretty quickly. But let's compare ln x and rad x. So the first one will be f, the second one will be g. Now if you look at their graphs, right, ln x looks like this, and rad x starts out a little higher. But that doesn't mean that g is growing faster. It's just higher up on the page, right? So what's going on with this gap between the graphs? Is this gap going to widen? Is this gap going to get narrower? What's going on? Does ln x ever crisscross pass through rad x? Like, does f ever cross g at some point? Right? These are interesting questions. But none of them are necessary because we have a rule. Let's just take the limit. What is LIM? X goes to infinity. ln x over rad x. I have no idea. Later on I'll show you how to rewrite ln x as a polynomial. But that's chapter 9. So what we're going to do is just L'Hopital. L'Hopital's rule. LHR. Okay, so this gives me 1 over x, and on the bottom 1 over 2 rad x. And if you do Miss Chen's little outer is the numerator, inner is the denominator trick, the outer is the numerator, the inner is the denominator. You can even use L'Hopital's rule a second time, or reduce it, doesn't matter. I'll do L'Hopital's rule a second time. you're going to get 1 over rad x over 1, and this clearly goes to 0. Okay, so it went to 0. What does that mean according to rule 1 today? The bottom function grew faster. So yeah, that means g of x grows faster than f of x in this problem. Therefore, g of x equals rad x grows faster than f of x equals ln x. The truth is, I challenge you to find a function that grows slower than ln. It truly is a very, very slowly growing function. When we get into chapter 9 and we study p-series integrals, you're going to realize that ln x is the slowest growing function we have. There's nothing like it. It's a very special situation. Okay? So, actually, you probably even understand it in section 8.4, which is starting tomorrow. Okay, so there's your rule, just a simple limit and one conclusion. Okay, sometimes what happens is they give you two functions and the limit is just too hard. So let me teach you how to cheat your way through that. Okay? So take a look at this problem. Compare f of x equals square root of x squared plus 5 and g of x equals parentheses 2 rad x minus 1 quantity squared. Now when I first look at this problem, I have no idea who grows faster. I mean, look at this. This is complicated, right? But something interesting popped out at me. Did you notice that when x is extremely large, the 5 really won't matter too much? Isn't that true? So like if you plug in 1,000, this gives you 1,000,005. The square root of 1,000,005 and the square root of 1,000,000 are pretty much the same. And if you plug in 1,000,000,000, this is 10 to the 18th plus 5, the square root of which is practically the same as the square root of 10 to the 18th. You see? So what I'm saying is this. As x gets massive, the 5 really doesn't matter. This becomes approximately rad x squared, which is what? X, right. And the same thing happens here. Look, if x is extremely large, the dominating term is the 2 rad x. This pretty much is negligible. And I just get 4x. You see? So when x is big, this is like x. And this is like 4x. I think they grow the same. Okay? Now to prove that, I need to do my test. Okay? So how am I going to do that? If I put these guys in ratio with one another, it's going to be really challenging to do this limit.
Can you do approximations?
Well, you have to be careful with how you show work in your limits too. Like limit work, you're not supposed to do stuff like this, guys. You're not supposed to go like that. You know what I mean? That's not showing your work. That's just thinking. Okay? So I can't like scribble stuff out, but what I can do is this. I believe that f of x is pretty much linear when x is large. So like I believe that this goes kind of towards f equals x when x is big. So I'm actually going to pick a brand new function, a third function, h, and that function is going to be x. Really simple. So I'm going to choose h of x to just be x. Now watch what I'm going to do. Here's my strategy, okay? First I'm going to show that f and h grow the same. This is my strategy. Problem solving involves coming up with an idea, right? I want to show that f and h grow the same. Then I'm going to show that g and h grow the same. Grow at the same rate. And then that's going to be pretty clear to me at that point that f and g would grow at the same rate, right? If f and h grow at the same rate, and g and h grow at the same rate, then it would stand to reason that f and g grow at the same rate, you see? All right, so let's try it. H is so easy to work with. All right. Let's give it a try. So the first thing I'm going to do is just do LIM f over h. and that's this thing. It's still a little tricky. Are you guys okay with this if I write this like that? You guys comfortable with me changing it to that? Does this bother anybody?
Why don't you just use L'Hopital?
I could use L'Hopital's rule.
That would just get rid of that.
You want to do that? Okay, I was going to rewrite it like this. Let's use L'Hopital's instead. That's fine. Great. So the derivative, you guys are so good at derivatives. The derivative of that numerator is going to be 2x over 2 rad x squared plus 5. The derivative at the bottom is 1. It's still a little awkward though. It's okay, that's a good idea, right? I still find this limit a little hard to work with. I think I'm going to go back to my original plan. I'm going to rewrite this as x squared plus 5 over x squared. Now I absorbed that bottom x into the radical, and of course I had to square it on its way in. But this reduces to 1 plus 5 over x squared on the inside. So this is just 1, and this is 5 over x squared. So it looks like this. And limits are so forgiving, I can actually save the square root for later and just do the limit on the inside first. Limits are like that. You can just kind of save the radical for later. Okay, so you'll notice that the inside is going to 1, right? The 5 over x squared is going to vanish, and you're going to get 1. So basically this becomes the question, what is the square root of 1? 1. Notice I just got a non-zero number. So f and h grow at the same rate. That was actually my plan. I was trying to show that first. So check. I just showed that f and h grow at the same rate. Now I'm going to show that g and h grow at the same rate. Okay. So let's do LIM, x goes to infinity. And this is, let me write one line of work before this. So this is LIM, x goes to infinity. I'm doing g over h now. I can do sort of the same thing here. I'll bring the x on the bottom into the square. So what I did is I square rooted it. I wrote this as square root of x squared. See? And then I pulled the square out. The inside of this collapses to 2 minus 1 over root x. Quantity squared. Because again, you can circle these, right? Break that up. I can save the square for the last step of the problem. So let's just bring that LIM on the inside here. Save the square for the last stage. And this gives me 2 on the inside and squared. So this comes out to 4. I just got a number. What does this tell us? Therefore, g and h grow at the same rate. Okay, so my final statement, and this might remind you of an old joke. The final statement is this. F and h grow at the same rate. We proved that. Check. G and h grow at the same rate. Except I didn't write the word rate. Getting too excited for this conclusion here. Check. Periods on the end of the sentences. Therefore, F and G grow Same. Great. Well, it might remind you of the old rule, if A equals B, then B equals C. I'm sorry, if A equals B and B equals C, then A equals C. Do you remember that old rule? Do you guys remember what that's called? Transitive property? Transitive, right? You get it? Transitive? Transitive. Transitive. Transitive property is used when you link two ideas together to form a third idea. In logic, it's also called syllogism. Maybe you've heard of that word too. But I always think of it as a train. So you've got fact A and fact B, and they're linking together. They're linking together to form, if A and B are true, then C is true kind of thing. That's the transitive property. And it reminds me of a train. So I sometimes call it the transitive property. Because you're linking ideas together in a chain or train-like fashion. That's the lesson. Okay, the hardest ones are the ones where the limit looks challenging and you're not comfortable with it, so you just pick a third function. So somebody asked me first period, how did you know to pick h equals x? And the way I'm going to answer that is, you don't always know you picked the right h. Okay? I chose h to be x, and the reason I chose it was because I believe this acts very linear when x is large. The 5 wouldn't matter, and this is grad x squared. Does that mean I'll choose h equals x on every problem? No. I'll just pick something that behaves like this at large values. Okay? You need to be comfortable with that when we do the direct comparison test in chapter 9. We do the same thing. We pick a sequence that's not mentioned that represents something like these. Okay? I believe that this is a good choice for two reasons. One, when x is big, this reduces to x. And notice I was actually getting numerical answers for my limits. That means I was doing it right. One last comment, and then we'll shut it down. Let's say you did this first limit, you chose your h, you're very proud of your h, you did your limit, and you got, listen, infinity. If you got infinity here, what that means is that f is actually growing faster than h. So before you proceed to go on to the next part, you need to realize that you're wasting your time. If you prove that this is infinity, then clearly f grows faster than h. If you then go down here and prove that this is infinity, which means g is growing faster than h, you know nothing about f and g. You've simply shown that f is a very fast-growing function, and so is g. How does that help you compare the two? That doesn't help at all. So you need to pick something that actually gives you results. I know that's really cart before the horse thing, but I showed you kind of how I figured out that h, and it was working. You can see the numbers. If both these come out to 0, that just means that you've picked an h that's really fast. How does that help you compare g and h, or f and g? It doesn't. So you can never prove a divergence from two divergences. We'll talk about that more in chapter 9.
So if you don't choose like a correct, like extra function, do you
have to start over.
Oh my.
But let me show you again how I picked it. I was looking at this term because that term is the only influential term when x is large. And then I skirted it, and I was like, oh, that's just x. That's how I picked this. Okay, yeah?
Is that the process you use to pick all of them? Just make x really large?
I do.
Okay.
But that can't suffice for my total work. I have to show all this garbage.
Yeah. But like, as far as picking h of x.
Yeah. I actually predicted that f and g grew the same in the first place. I said if I make x big, that's going to come to x. That's going to make 4x. So I knew that x and 4x would be the same. See what I'm saying?
Yeah.
But the proof is the work.
Yeah.
Yeah, so I have to
Same
show
with
it.
the homework, like,
On homework, try to show it.
okay.
Yeah, show it out. Question, and then we'll do Q&A. Yeah.
So what happens, so he says to compare them, right? Are you going to always show that they're the same rate? Is that generally what they're going to ask you?
Yeah, my instruction, I got lazier. My instructions should say either decide which function grows faster, or show that f and g grow at the same rate. But it's a very specific set of work. It's not like, oh, that's my feeling. I feel this way. It doesn't work, okay? So we learned a couple new things today. We learned that you can use a limit to prove which grows faster. We also learned that ln of x is the slowest growing function we have, okay? Which opens up a question, what's the fastest growing function? We're not quite ready for that yet. But okay, I'm going to stop the video. Do you guys have any questions on either of the book pages for 8.1 or 8.2?